Hello everyone, this is Roushan. Welcome to session 8, which is based on week 8. So in the previous session, I have covered week 7 lectures, and in this session we will see lectures based on week 8. So let's start the today's session. So in week 8, 3 lectures are there, lecture 21, 22 and 20. So lecture 20 and 21 is based on the extension, torsion, inflation in hollow cylinder. I am just writing here lecture week 8. In this week 8 we have 3 lectures. First lecture is extension, torsion, inflation. Extension, torsion, inflation in hollow cylinder. The second lecture is follow-up of this lecture, which is on solving governing equation. Solving governing equation based on extension, torsion and inflation. Based on extension, torsion and inflation. The third lecture is basically a problem solving lecture where 3 or more different problems were solved in these lectures. So basically I will not cover this lecture because this session is basically the problem solving session and I do not solve the same problem here. So this lecture is basically problem solving problem involving torsion of shafts. So before going to the problem solving session, first I will briefly explain and the important concept which were covered in the lectures in these 2 lectures. So in the starting of these lectures, actually the concept of torsion, inflation and extension were discussed. So basically in these lecture we derived a equation of equilibrium in the case of extension, torsion and inflation. So I'm just writing the equation here which can be used in solving the problem, which will I discuss later. So first concept that is being discussed there is the twist. So twist is nothing but basically a rate of change of cross section, rate of change of angle of cross section, rate of change of angle of cross section. The angle by which the cross section, the rate by which the angle of the cross section changes is called the twist, and it is given by, so twist is basically represented by total change in angle upon total length, which is represented by omega. Total change in angle is represented by omega and total length is represented by big. And if you want to find the rotation of the cross section at any z, so it is given by rotation of cross section at any z, which means suppose we have a cylinder and the length of the cylinder is along the z axis. So it is given by alpha in terms of z is given by omega by L into z. So this is the rotation of the cross section at any z. At z equal to 0, basically the rotation is 0. So equilibrium equation, next I will write equilibrium equation for extension, torsion and inflation. So the equation that were derived in these lecture is written here. So I just write the equation here. For detailed derivation, you can refer the lecture. So we have three different equations. One is along r direction, the second is along the theta direction, the third is along the z direction. Del sigma r upon del r plus sigma r minus sigma theta theta upon r plus br equal to 0 is equal to rho ar if acceleration, radial acceleration is also present. So here ar is the radial acceleration, br is the body force along the radial direction. B theta equal to rho a theta, and the third one is sigma del sigma zz upon del z plus bz equal to rho az, where az is the acceleration component of acceleration along z direction, and the theta is the component of acceleration along theta direction, and b theta and bz are the body forces in theta and z direction. So this is the complete governing equation for the case of extension, torsion and inflation. So here this equilibrium equation is derived based on the several assumptions such as axial homogeneity and axisymmetry. So with these two assumptions, we will basically we have obtained the following these three equilibrium equation for the extension, torsion and inflation. And suppose if we are dealing with the zero gravity and static problem, suppose there are no body force present in the system, and also it's a static problem, that is our body is static in equilibrium. So this equation will become for a static and zero gravity problem. The above equation will become the following equation, that is del sigma rr upon del r plus sigma rr minus sigma theta theta upon r equal to 0, and the second equation that only exists is del sigma zz upon del z equal to 0. So these two equation only will remain in the case of a static and zero gravity problem. So here you can easily see that if the body force is not present, so b theta is 0, and if we are dealing with a static problem, then acceleration, radial acceleration, tangential and radial component acceleration, theta component acceleration and z component acceleration also going to be 0. So in that case, this equation, that is equation number second, will vanish completely, and the only two remaining and only two equations will remain, that is these two equations. So I just wrote here. So this is the case when there is no body force present in the system and the problem is static. Now the expression, basically we have to derive the expression of the radial stress, radial normal stress, and hoop stress and circumferential stress, and sigma zz, that is axial stress. So basically we have to find these three stresses, normal stresses, to deal with any kind of problem. So I am not deriving the whole stress equation. I'm just writing the stress equation which is obtained after several mathematical formulation. So the final expression for thick cylinder that is expression for sigma rr and sigma theta theta. So the final expression that is obtained for the thick cylinder, uh, the expression of sigma rr and sigma theta theta is given by these equations. So sigma rr is given by a by 2 plus b by r square, where r is a radial coordinate at any particular radius. Sigma theta theta is given by a by 2 minus b by r square, where a and b is given by, so this is the relation for sigma r and sigma theta theta. And suppose if we are considered uh, a thick cylinder or a hollow thick cylinder where r1 is the inner radius of the cylinder and r2 is the outer radius of the cylinder, and the r2 minus r1, that is r2 by r1 is less than 10. That means this is not a case of the thin cylinder. So in that case, the value that is obtained for a and b is given by, for thick cylinder problem, and for the case of torsion and inflation, so we need three boundary condition, and after applying the boundary condition we get the following expression for a and b. So a, the value of a is given by 2p r1 square upon r2 square minus r1 square, and the value of b is given by minus p r1 r2 square upon r2 square minus r1 square. So this is the expression for a and b for thick cylinder problem. Here we also derive that the sum of the radial and the tangential stress, that is the sum of these two normal stresses sigma r and sigma theta theta, that is sigma rr plus sigma theta, is nothing but equal to a, which is a constant. So the sum of sigma r and sigma theta is actually a constant. Here also from this relation also you can see from the figure that it becomes a constant value, that is equal to a. Here P is the pressure inside the cylinder. P is nothing but the pressure acting inside the cylinder. So this is the case for thick cylinder problem if you are dealing with the extension, torsion, inflation problem. And if we have a hollow cylinder with radius, internal radius r1 and outer radius r2, and considering that r2 by r1 is less than 10, that means it is a case of the thick cylinder, then the stresses, that is sigma rr and sigma theta theta, is given by these two relation. Sorry, it's given by this two relation. Okay. The next thing which I want to discuss, which is already discussed in the second lecture, that is lecture number 21, which is based on the torsion, that is the equilibrium equation, solving governing equation for the case of torsion. So first of all, I would like to know you the formula for the torsion. So it is given by, that is the torsion, where basically it is called as torsion formula. So it is given by T equal to Gj omega by L, where G is the shear modulus of the body, and as you know that omega by L is nothing but it is called twist, or we say rate of change of rotation of the cross section. And so this is the formula for torsion, where T is the torque. So if we rotate the two cross section, the two ends are rotated inversely, suppose the left end rotated counterclockwise, so the right end rotated will rotate by clockwise direction. Then it induces some twist in the cross section. That is, there is a change in the angle of cross section, so it induces actually torque. So to find the value of the torque, we can use this formula, which is basically T equal to Gj by L, Gj omega by L. Also from here we can infer that omega, which is the rotation of the cross section, is given by TL upon Gj. So it is called end-to-end rotation, end-to-end rotation. So this is all about lecture number 2021 and 22 lecture based on the problem solving. So you can refer those lectures to see the problem that is solved already in the lecture. So I will solve some new problem based on the this concept. So let's start the problem solving session now. So the first question itself is based on the extensor torsion and inflation of the hollow cylinder. So the question number 1 is, I am writing the question. So this is problem number 1. Suppose a solid disk of radius r and a hollow disk of inner radius r1 and outer radius r2. Are shrunk fit together. Assuming that r is greater than r1. Okay. Further assume that no external pressure is applied. No external pressure is applied on the outer hollow disk. On the outer hollow disk, and that no axial displacement is allowed. In the two disk. And also let the two disks be made of same material. Let the two disks be made of same material. So the question is, also it is mentioned in the question that only radial displacement UR generates in this case. So the question is, first question. So basically this question has 3 parts. The first part of this question is write down all the boundary conditions. Write down all the boundary conditions. Write down all the boundary conditions, interface condition, required to obtain variation in radial stress sigma rr in the two disk. The second part of this question is solve the governing equation. Solve the governing equation and obtain expression for sigma rr in the two disk. And the third part of this question is obtain expression for circumferential hoop stress 2. Circumferential of hoop stress 2. So let's begin the solution for this question. So the question says, I am repeating once again the question. The question says, suppose a solid disk of radius r and a hollow disk of inner radius r1 and outer radius r2 are strung fit together. Assume r is greater than r1. Further, assume that no external pressure is applied on the outer hollow disk and that no axial displacement is allowed in the inner two disks. Let the two disks be made of the same material. Only radial displacement UR generate in this case. So here is the assumption that only radial displacement generate in this case, that is UR only generates here. So the first part of this question is write down all the boundary conditions, interface condition required to obtain variation in radial stress sigma rr in the two disks. And the second part of this question is solve the governing equation and obtain expression for the sigma rr in the two disks. And the third part of this question is obtain the expression for circumferential or hoop stress. So we have two disks basically. So one is a disk of radius big R. This is a solid disk of radius big R, and the other one is a hollow disk of inner radius R1 and outer radius R2. So we have another disk of inner radius R1 and outer radius R2. Here it is mentioned that R is greater than R1. That means this disk has been fitted to the hollow disk. Actually, the radius of this solid disk is greater than the inner radius of hollow disk, and then the question arises: how this solid disk be fitted inside this hollow disk? So basically, in general, two disks are inserted together by using the heat treatment. So suppose if we if we heat this solid disk and compress it, then it compresses at that time when it very hot. Then we fitted this disk into this inside hollow part of the hollow disk, and after this solid disk fit into the hollow disk, then we cool the disk, and after cooling treatment, the solid disk actually expand, and and the hollow disk try to contract it. So basically these two disks rigidly fitted within one another. So in this way we can say that the radius of big R can be fitted to the hollow disk. So during this process, what happened actually when we heat these two disks? So actually this disk has some stresses present inside it because we have heated this disk. So there, due to that heat treatment, stress will generate inside the hollow disk, and also because this solid disk is fitted inside this hollow disk, and when it contract after cooling, when it contract, then some pressure also acting inside the on the solid disk. So this we can say that I am draw one figure to better, so that you can better understand. So just suppose this is a disk, and this is same disk here also. So basically, when this disk is inserted into inside this disk, when this disk is inserted inside into this disk, actually this solid disk experience some pressure coming from outside. So it experience some pressure. And this disk trying to expand, the hollowed part of the disk is trying to expand, because to maintain equilibrium, if this disk, if the pressure is acting downward in the solid disk, then pressure is acting must acting upward in the hollow disk. So in this case, the pressure is acting from inside. Suppose this is pressure P star. And initially the radius is actually R. Okay, the radius is actually big R at the initial case, and when we do the heat treatment and insert the solid disk into the hollow disk, so there is some radial displacement also happen due to the outer inner radius of the hollow disk. So we can write simply here U at R, that means radial displacement at 1 due to radius R. Okay, and this is a hollow disk, so inner radius is initially at R1, and due to the expansion, due to the pressure exertion in the inside the hollow disk, there is some radial displacement occur, which is given by U2 of R1. Okay, so I am denoting 1 is for the solid disk. Yeah, the number superscript 1 shows here, so it basically represent the displacement, radial displacement corresponding to solid disk, and this UR2 represent radial displacement corresponding to hollow disk. Okay, so the stress generate on this disk, suppose radial stress on this disk is denoted by sigma RR of 1, and the radial stress generated on this disk denoted by sigma RR 2. Now, so I am just writing here shrink fit insertion is usually performed by heat treatment that is heating that is by heating the hollow disk that is by heating the hollow disk. So on heating the hollow disk, basically it expands its diameter so that it fitting over the solid disk, and after that we basically have to cool the disk, and then cooling it. So this is a process through which we can insert a solid disk into a hollow disk. So after the insertion, both the disks actually are in the pre-stress condition, because without giving any deformation, without giving any external load, it's actually is in tension or compression from inside, because we have forcefully inserted the solid disk into the hollow disk, so it's in the pre-stress condition. So we can say we also write here that solid disk and the hollow disk solid disk and hollow disk are represented by superscript 1 and 2 respectively. Okay, so basically due to this, hollow cylinder is in pre-stress condition. So due to this, actually the hollow cylinder is in pre-stress condition, and we have to find that stress only, that is sigma rr acting on the inner hollow cylinder, and sigma rr acting on the solid disk on the outer surface. So as we know that in the lecture itself we have derived the equilibrium equation and the radial stresses, that is sigma rr and sigma theta theta, for the solid disk when it is acting by a pressure from inside. When suppose there is a solid disk, there is a hollow disk of finite thickness, that means this is a case of the thick cylinder, and when pressure is acting from inside, so we have derived already the expression for sigma r and sigma theta theta. The expression which we derived in the lecture is already I mentioned in the starting of this lecture, which I again write here. So for thick cylinder, we have already derived sigma r at 1, that means at the solid disk in terms of r is given by a by 2 at 1 plus b at 1 by r square, and sigma r, that means sigma r acting on the hollow cylinder, is given by a by 2, where a and b are the constants in terms of the hollow cylinder. So a by 2 plus b by r square, or in terms of radial displacement, or in terms of so here we can write that the radial equation we can also write it in terms of radial displacement. So for in terms of radial displacement, it is given by ur at 1 is given by c1 at r by 2 plus d1 at r by 2. Okay, I hope I am audible. Now the next case is you are at 2. You are at 2 at R equal to C at 2, C at 2, R by 2 plus D at 2 upon R. And for the current problem, where axial strain, here we already mentioned the question, that is there is no displacement along z direction. It's already if you see the question, only radial displacement generate in this case. So there is a assumption that only radial displacement generate in this case. So for this case, axial strain will be 0. So we can say that as axial strain, that is epsilon, equal to 0, we have A at 1, or we say A at I, is given by 2 times lambda plus mu times C1 Ci, and B at I equal to minus 2 mu di. So the value of these two expression of these two A and B are already derived in lecture. So these two expressions are already derived in the lecture. So you can go through and see the how it come, the final expression of A and B. So now here, if you see our expression, we have 4 independent integrating constant, which will require actually 4 boundary conditions. So if you see the knowns, we have A, B, C and D. So basically we have 4 unknown, and for this we require 4 boundary conditions. So the boundary conditions, so the first question basically, write down all the boundary condition, interface condition required to obtain variation in radial stress sigma r in the variation. So for obtaining the sigma rr value, so sigma rr have 4 unknowns, A, B and A and B of 2. So to find out the stress expression, radial stress expression, we have to write down the boundary condition. So basically we have 4 unknowns, so we have 4 boundary condition. So the first part of this question is boundary condition. So we know that at the interface there is a continuity. At the interface, there is a continuity, stress continuity. Radial stress continuity. So for this we can say that the first boundary condition will sigma r at due to the solid disk is same as sigma rr due to at hollow disk. So this is basically sigma rr, and sigma rr 1 and 2 represent radial stress at the interface. Radial stresses at the interface. So this is the first boundary condition. So how it comes? So it comes from the continuity of radial stress. The second boundary condition is, we already mentioned that for the sink fit condition. So this actually inserted into this hollow disk. The solid disk is inserted into the hollow disk. So we can say that R plus UR at 1 is same as R1 plus UR at 2. So this comes from string fit condition. So we have these two boundary conditions. Another boundary condition is, as already mentioned in the question, there is no external force applied across the outer boundary of this hollow disk. So there is no traction. This is actually no traction present because there is no force acting from the outside. So we can say that there is a traction free boundary condition. That means stress 2, that means the hollow disk, on the hollow disk from the outside of the cylinder, that is at R2 equal to 0. So this comes from traction free boundary condition. And the fourth part is, as you see that the expression for sigma r. So here actually there is a expression in the expression of sigma r, there is a b by r square, and at r equal to 0 we have basically infinite stress. If we take r equal to 0, that is at radius equal to 0, we have infinite stress. So we have only finite stress value present at the center of the disk. So we can say that sigma r at 1 at r equal to 0 is 0. So sigma r at r equal to finite, and that is why we can say that UR at r equal to r is actually 0. So we have these 4 boundary conditions. So this is the first part of the question. The second part of the question is, solve the governing equation and obtain expression for sigma r in the two disk. So we have to solve the governing equation and find the expression for sigma r in both the disk. So the second part of the problem is, so from the lecture we can find that the expression for sigma r at 1 at radius r is given by lambda plus mu c1 minus 2 mu d1 upon r square, and similarly sigma r on the hollow cylinder from inside is given by lambda plus mu c2 minus 2 mu d2 upon r square. Now apply boundary condition. So we get actually, so on applying this boundary condition we get sigma r at 1 equal to 0 is finite. So this value to be, for this two value to be finite, we can say that d1 equal to 0. Okay. The second is sigma r at 1 equal to sigma r at 2. So we can say that lambda plus mu c1, so from here d1 cancel out, lambda plus mu c1 equal to lambda plus mu c2 minus 2 mu d2 upon r square. We also have one more boundary condition, that is boundary condition 2, that is R at u1 plus R equal to u2 R1 plus R1. So it will become C1 R by 2 minus C2 R1 by 2 minus D2 upon R1 equal to R1 minus R. Okay, so it finally become, when you apply this boundary condition, that is sigma RR at 2 at R2 equal to 0, that is traction free boundary condition. So on applying this condition, we get lambda plus mu C2 minus 2 mu D2 upon R2 square equal to 0. Okay, now solving these three equations, that is equation number 1, 2 and 3. Equation 1, then equation number 2 and equation number 3. After solving these three equations, solving equation 1, 2 and 3, we will get, because if you see these three equations, we can see that we have three unknowns, C1, C2 and D. So we have three unknowns here, C1, C2 and D2. So on solving these three equations, we finally get the expression for C1, C2 and D. We obtain C1, C2, D2. And if we know the value of C1, C2 and D2, then finally put these values in the radial stress expression. So when we get this expression in the radial stress expression. Now the third part of this question is obtain the expression for circumferential stress. That means we have to find the expression for sigma theta theta also. So once unknowns, once the value of constants are known, then simply we get the circumferential stress. Circumferential stress, that is sigma theta theta at 1 equal to lambda plus mu times C1 and sigma theta theta at 2 lambda plus mu times C2 plus 2 mu D2 upon R square. So this is the expression for sigma theta theta for the two cases, for the two discs, the solid disc and the hollow disc. So I think I have solved. So I am not writing the expression for the radial stress. You can simply solve this problem. I just basically give the overview how you will solve this question. So this question has three parts. The first part is to write the boundary condition for this problem. So we have, and I mentioned that there is only radial displacement here. So Based on this assumption, we have first write down the expression for the radial stress and the radial displacement in terms of A and B. So this is already derived in the lecture. You can go to the lecture and see the expression for this, how it comes. Then after that, we have to write the boundary condition for solving this unknown. Basically, we have four unknown, and for to find the exact expression for radial stress, we have to find the value of these unknowns. So we need boundary condition to solve the problem. So we have four boundary conditions. The first boundary condition is due to the continuity of radial stress at the interface. The second boundary condition is the sink fit condition, and the third boundary condition comes from the traction free boundary condition, and the fourth boundary condition comes from the finite displacement at the center. That means at radius equal to 0. So this four boundary condition, using this four boundary condition, we can find the constants value, that is C1, C2 and D2. When we find these constants, we basically put in the expression for sigma rr and sigma theta theta, and then we can find out the value of radial. Then we can find the expression for radial stress and the circumferential stress, sigma rr and sigma theta theta respectively. So this is the question. So how you can solve this type of question? I have already given the whole concept. Now move on to the next part of this question. Next question, basically problem number 2. So problem number 2 is derive expressions for sigma rr, sigma theta theta and sigma zz for thin pressurized tubes with application to pressure vessel. So we have already derived the expression of pressurized tube with application to pressure vessel for the thick cylinder, but here we have to derive expression for sigma rr, sigma theta theta for thin pressurized vessel. Okay. So there are two different ways to find the expression for sigma r and sigma theta theta and sigma zz. So for thick cylinder, for thick pressurized tubes, we derived in the lecture itself the expression for sigma r and sigma theta theta. So the solution for this question is, so I'm basically first I will take the expression for thick pressurized vessel and reduce that expression for the thin pressurized vessel. Later on, I will completely derive the expression for thin pressurized vessel. I will not take help from the expression for thick pressurized vessel. So we will go through two different approach. The first approach is using deduce the expression from the thick pressurized vessel, and the second approach is completely derive the expression for thin pressurized vessel. So the first part, I'm just draw here the thin pressurized vessel. Suppose the thickness of this hollow cylinder is T, and as it is a pressurized vessel, so pressure is acting from all the pressure is acting from the inside of the cylinder to all the faces. That means here also pressure is acting, here also pressure is acting, here also pressure is acting, and here also pressure is acting. Suppose pressure P is acting from all around, and suppose this is along, the length is along the z direction, and suppose this is the outer radius R2, and if we draw the inner radius, so this is the inner radius R1. So for thick pressure vessel, we already write the expression for sigma r and sigma theta theta. So here this is the expression. So A is given by A is given by 2p r1 square upon r2 square minus r1 square, and B is given by p times r1 square r2 square upon r2 square minus r1 square. Similarly, sigma r is given by A by 2 plus B by r1 square, and sigma theta theta is given by A by 2 minus B by r2 square. Now if we reduce it to thin pressure vessel, so here for thin pressure vessel, that is R2 is approximately equal to R1, and T is given by R2 minus R1. So if we substitute this assumption in this two, we will get A equal to 2p R1 square upon R2 plus R1, R2 minus R1. And what is R2 minus R1? R2 minus R1 is basically T, and R2 is approximately equal to R1. So basically in this case we will get 2p R1 square upon 2R1T, which finally give us p R1 upon T. So this is the expression for thin case when we are dealing with thin pressure vessel, where the thickness is very less and the outer radius is almost equal to the inner radius, and the value of P is minus P R1 square R2 square upon R2 square minus R1 square equal to minus P R1 square R2 square. And what is R2 square minus R1 square? We can write it using this identity, this actually relation R2 plus R1. R2 square minus, basically using this relation, A square minus B square is A plus B into A minus B. So R2 plus R1 into R2 minus R1, and R2 is approximately equal to R1, so we can write minus P R1 square R2 square, and R2 plus R1 is approximately R2, yeah, R1, we can say anything. So 2R1, and what is R2 minus R1 is T. So R1 cancel out, and here also if we say R1 is same as R2, so R1 square upon 2R1T is finally gives us minus P R1 cube upon 2T. Okay, so this is the final expression for B. Now the expression for sigma RR is given by A by 2 plus B by R1 square. So what is A here? So A is finally P R1 by T, and what is B here? Minus P R1 cube upon 2T R1 square, which finally give us P R1 upon 2T minus P R1 upon 2T. which finally results equal to 0. So here we find that sigma RR value for thin pressure vessel is finally coming out to be 0. And what about sigma theta theta? So sigma theta theta is given by A by 2 minus B by R1 square equal to PR1 upon 2T plus PR1 cube upon 2T R1 square, which finally results in PR1 upon 2T plus PR1 upon 2T, which finally gives us PR1 upon T. So sigma theta theta for thin pressurized vessel is given by PR1 upon T. Okay. And now what about sigma ZZ? So sigma ZZ is finally given by this expression. So actually, if we see the value of sigma ZZ, so pressure is acting on the pressure is acting from the inside surface to the outside surface, and there is a possibility of a stretch. So we can say that as the thickness is very small, the thickness here is very small, so we can say that sigma ZZ does not vary through the wall thickness. So here it is an assumption that sigma ZZ doesn't vary. Sigma ZZ does not vary through the wall thickness. And accordingly, when no external force, because here there is no external force acts on the cylinder, when no external force acts on the cylinder, we have sigma ZZ is given by pi R1 square P upon pi R2 square minus R1 square, which finally results in P R1 upon 2T for thin cylinder. So this is the case for sigma ZZ. This is how we obtain the value of sigma ZZ. So this expression is already right in the lecture. You can go through and see the exact derivation how it comes. So this is one way to find the value of sigma RR, sigma theta theta and sigma ZZ for thin pressurized vessel. The other way is to directly obtain the expression of these stresses, assuming that the thin cylinder case. Okay, so let's using that case the second approach. So I am now using here second approach. So basically I am using the balance law. So in this approach we are using the force balance. So basically we are balance the force from inside and the outside of the cylinder. So in this way we can find out the stresses present in the cylinder. So first of all, force balance along z direction. So if we do the force balance along z direction, we will get, so I'm drawing again the figure. I just copy that figure. So if we do the force balance along z direction, so there is a pressure acting from inside, and if we see the stress, that is the sigma zz, so it is acting along this direction. So if we do the force balance in z direction, so it is given by 2 sigma zz into this complete, this actually a, this actually a hollow cylinder now. So actually the circumference, that is 2 pi r into thickness, give us the area. So and it is acting from both the directions, so it is given by 2 sigma zz into 2 pi r1 2 pi r1 into T, which is equal to this pressure acting from the inside, which is given by P into pi r1 square. So if we calculate this, we will get finally sigma zz is equal to P r1 upon 2T. So if we see the expression, if you match the expression of this sigma zz with the above found, we see that both of these are same. So this is the way through force balance we can find the value of sigma zz stress, that is the stress along z direction. Now coming to sigma theta theta. So sigma theta theta, so basically this is a cylinder, so we have to cut along the radial direction. So basically we have to cut the cylinder from the half, that is the mid plane. So if we cut the cylinder, that is a thin pressurized vessel, so it will ultimately look like this way. So actually this is sigma theta theta, and pressure is acting from inside. So sigma theta theta coming all the direction. Okay, and if we do the force balance along theta theta direction, so we will get finally sigma theta theta times, this is the length of the cylinder, and we have two different length L, and from this side L, that is 2L times thickness is given by pressure, and where the pressure is acting along theta direction is P times whole the circumference. That means two R1 into T. Okay, sorry, L, not T, because this is L and this is R1. So the complete pressure acting on the surface is given by, so we have basically balanced the force, we have do the force balance along the y direction. Okay, and if we do the force balance along y direction, so basically pressure is acting upward and it's along the whole plane. So if we take this plane, so the area of this plane has to be taken, which is 2r1 into L, and this is the 2lt because the tangential stress, because the circumferential stress is only acting at the edges, that means L into T, and we have two edges. If we cut the cylinder by half in from the mid plane, we see that we have two different edges, the left one side and the right hand side edges. So basically that's why it has 2L into T. Basically it has LT plus LT, and that's how it become 2LT. So in this way we can find the value of sigma theta theta, which is given by PR1 upon T. Now the last one is sigma RR. So to find out the sigma RR, as we see that this is actually, this case is actually this is a case where the traction free boundary condition is present. So you can see that there is no stresses, there is no force acting from the outside, and we can say from this equation that due to homogeneity, of stress, due to continuity of stress along the radial direction, the inside radial stress also must have zero value, because from the outside it has no stress, there is no stress because there is no force acting from the outside. So we can say that when we consider outer traction free surface, so from outer traction free surface there is no stress present, there is no force acting from outside, and that's why from the outside there is no stress, that is sigma RR equal to 0, and from the inside there is a pressure acting here. From here sigma RR equal to 0, and from here sigma RR equal to minus P, and from inside, and the internally pressurized surface where sigma RR equal to minus P. So sigma RR varies from minus P at inner surface to 0 at outer surface. And here, if you see that R1 by T is very greater than 1, because T is very small, and that's why it's a case for thin tube. So for thin tube case, the value of PR1 upon T and PR2 PR1 upon 2T for hoop and axial stress respectively will be very large compared to P. Here you can see that if you see the cylinder, that is the thin pressurized cylinder, we can see that from outside, because it's a traction free boundary condition, there is a traction free boundary condition, so there is no radial stress coming from outside. But if you see the inside, from inside of the cylinder, we see that a pressure is acting from the inside cylinder, and therefore it has stress minus P, which is acting in the outward direction. So we can say that when we see radial stress varies from minus P from the inner surface to the zero value from the to the outer surface. But here if we see the hoop, or we say circumferential stress, and the axial stress value, that is sigma z, that is axial stress, which is given by PR1 upon 2t, and the circumferential stress is given by PR1 upon t. If we see these two value, then we can say that these two values, PR1 upon T and PR1 upon 2T, is very, very large as compared to P. Why I am saying that? Because R1 upon T and R1 upon T is itself a very big value. Here R1 upon T is itself a very big value. And that's why PR1 upon T and PR1 upon 2T is a very big value as compared to P, because there is a very less significant contribution of P in the hoop stress and the axial stress value. And therefore we can say that as P value is very, very less as compared to PR1 upon T and PR1 upon 2T, and therefore sigma RR is neglected to be 0. Sigma RR is neglected and set to 0. Okay, so these are the two way through which we can solve this question, that is for the problem of thin pressurized vessel. So one way is to go with the thick pressurized vessel formulation, and assuming that R1 minus R2, that is R2 minus R1 is equal to T, and R1 is approximately equal to R2. And based on these assumption, go through the entire process of deriving the result, and then we finally come out to the final expression of sigma r and sigma theta theta and sigma zz for thin pressurized vessel. The other way we can derive it through the force balance equation. So basically we have to we have to do force balance in all the three directions, and through that we can derive the expression for sigma r and sigma theta theta and sigma zz. So these two different approach you can go through. So this is a very important question, and that type of question is frequently asked in various competitive exams. So yes, you can follow this question. Now move on to the next question, which is a simpler one based on the torsion of shaft. So this is problem number 2, and now we are solving problem number 3. The question says two shafts AB and BC of equal length and diameter D and 2D are made of same material. They are joined at B through a shaft coupling, while the ends AR while the ends A and C are built as cantilever. While the ends A and C are built in cantilevered. A twisting moment T is applied to the coupling. A twisting moment T is applied to the coupling if TA and TC represent the twisting moment find the relation between find the relation between TA and TC. So I am repeating the question once again. So the question says two shafts AB and BC of equal length and diameter D and 2D respectively are made of same material. So there are two shafts AB and BC of equal length and both have different diameter. The first shaft has diameter D and the second shaft have diameter 2D, and they both made from the same material. They are joined at B through a shaft coupling. So they are joined together through a shaft coupling. While the ends A and C are built in cantilever, while these two ends are cantilevered, a twisting moment T is applied to the coupling. If TA and TC represent a twisting moment, find the relation between TA and TC. So if TA and TC represent the twisting moment, so we have to find the relation between TA and TC. So for the reference, I am drawing one figure. So we have two shafts. TA and TC. And this is joined from a coupling. Both have equal length L. It has diameter 2D and it has diameter D. Okay. So we have to find the relation between A and C, TA and TC. So as the rotation, so here because a twisting moment is applied through a shaft coupling, T is applied basically to the coupling. So on applying this T, we basically, and this it's also mentioned in the question that these two ends are cantilevered. Okay. So if we twist from the in between, if we twist the two shafts, actually equal rotation in both the shafts will happen because two shafts are cantilevered, and if we twist, if we provide a torque in between through a coupling, we can see that there is a equal rotation, on both the shafts. So here we can say that rotation on both the shaft is same. So here rotation on both the shafts are same. That means omega on AB and omega on BC is same, which means, and what is omega? Omega is basically TL upon GJ. And what is J for circular cross section? So J for circular cross section is given by pi by 32 d to the power 4. So basically T1 L1 upon G1 J1 equal to T2 L2 upon G2 J2. And it's mentioned in the question that T1 is basically TA, L1 is L, G1, both the shaft are made of same material. It's given in the question already, so I am writing here just G. J1 is given by pi by 32 d to the power 4. And what is T2 is T2 is TC, L2 is L, G2 is G, and J2 is pi by 32 2d to the power 4. So LL cancel out, GG cancel out. So the only thing that is remain 32 will cancel out. TC upon 16. So that means TC equal to 16 times TA. So this is the final relation for TC and TA. Okay. So this is question number 3. Now move on to problem number 4. A torque T is applied at the free end of a stepped rod. A torque T is applied at the free end of a stepped rod of circular cross sections as shown in the figure. The shear modulus of the material of the rod is G. The angular twist omega at the free end is so the question is, we have 4 options for this question. The first option is 32 TL upon pi G t to the power 4, 18 TL upon pi G d to the power 4, 16 TL upon G d to the power 4, and the fourth option is 2 TL upon pi G d to the power 4. So we have question: a torque T is applied at the free end of a stepped rod of circular cross section as shown in the figure. So we have figure also. Sorry. So the question says a torque T is applied at the free end of a stepped rod of circular cross section as shown in the figure. So we have a stepped rod of length L. So basically what is a stepped rod? The stepped rod is a rod in which two rods are attached with two different, maybe made of same material or maybe of different material. So here two different rods are attached together. The first rod has diameter 2d and length L. The second rod has have diameter d and length L by 2. And the question says torque T is applied at the free end of a stepped rod. So a torque T is applied at the free end of the stepped rod. The shear modulus of the material of the rod is G. Both the rod have same material, that is shear modulus G. The angular twist omega at the free end. So total angular twist at the free end is given by the equation. So we have to find out the angular twist omega at the free end. So first, if we twist from the free end, if we provide torque at the free end, we have to find the rotation from this one and from this one also. That means we have to sum the rotation due to rod 1 and rod 2. So suppose this is rod 1 and this is rod 2. So, and torsion formula, through torsion formula we know that T is equals to G omega by Lj. Sorry, TL upon Gj. So we can say that angular twist omega at the free end is given by omega at 1 rod 1 plus omega due to rod 2, which is given by T1 L1 upon G1 J1 plus T2 L2 upon G2 J2. T1 is same because twist is same in both the rod, because here also twist is given if we know the balance equation. So there is in all the length, all along the length, a uniform twist is given, that is T. So T, L1 is L, G1 is G, and what is J? 1, J1 is basically pi by 32, 2d to the power 4. Okay. Plus T2. T2 is T, L2 is L by 2, and G2 is G, and J2 is pi by 32, d to the power 4. So 32 TL upon pi d to the power 4 is taken as common. So what will left? 1 by 16 plus 1 by 2, which finally gives us 32 TL upon pi d to the power 4 into G 9 by 16, which is nothing but 18 TL upon pi d to the power 4 into G. So the final rotation is given by 18 TL pi d to the power 4 into G. So this is the correct answer for this question, and it matches with option number B. So the correct answer is option number B. So this is a question based on the torsion of shaft. Now, the next question is basically a multiple choice question. So I'm writing the question here. Problem number 4. I think this is problem number 5. Yes, problem number 5. In case of torsion of circular shaft, in case of torsion of circular shaft, the first question is different cross section of the shaft, different cross section of the shaft rotated by same angle. The second option is different cross section of the shaft are rotated by different angle. Different cross section of the shaft are rotated by different cross section of the shaft rotated by different angle. The third option is the shaft gets stretched. The shaft gets stretched. And the fourth option is the shaft will not stretch. The shaft will not stretch. Okay, so let's come to the question. In case of torsion of circular shaft, whenever we provide some torsion to a circular shaft, what will happen? The first option says different cross section of the shaft rotated by the same angle. No, this is not the correct answer, because whenever we provide torsion to any circular shaft, every cross section of the circular shaft rotated by different angle. So this is incorrect option. The second option says different cross section of the shaft rotated by different angle. Yes, this is absolutely correct question answer. So yes, every cross section of the shaft rotated by a different angle. The shaft gets stretched. No, this is also not correct, because whenever we provide twist, whenever we provide torque to any circular shaft, it doesn't get stretched. The fourth option is the shaft will not stretch. Yeah, this is correct option. So these two options are correct. Now the second question, problem number 6. In case of axisymmetry problem, in case of axisymmetric problems, the first option is displacement component depends on theta. Displacement components depends on theta. Displacement component independent of theta. Geometric displacement component depends on geometrical properties of material. Displacement component depends on geometrical properties of material. And the fourth option is none of these. So this question is based on the axisymmetry problem. So the question is, in case of axisymmetry problem, displacement component depends on theta. No, that's not correct, because in axisymmetry problem we assume that the displacement component is independent of theta, which is the next option, that is option number B. So it's correct. The third option is displacement component depends on geometrical properties of material. No, it's independent of geometrical properties of material. And the fourth option is none of these, because one of the option is correct, so none of these is also incorrect. So this is all about question number 6. Now question number 7. Problem number 7. So problem number 7 is shear strain. No, this is not. Which of the following statement is or true for extension, torsion, inflation of hollow cylinder? The first option is sum of radial and hoop stress is constant. Sum of radial and hoop stress is a constant. The second option is radial and hoop stress does not vary individually. Radial and hoop stress does not vary individually. Sum of radial and hoop stress is not a constant. And the fourth option is radial and hoop stress vary individually. Radial and hoop stress varies individually. So the question is, which of the following statement is or correct or true for extension, torsion, inflation of hollow cylinder? Okay. So the first option is sum of radial and hoop stress is a constant. So yes, it's a correct option, because the radial and the hoop stress, when we sum over these two stresses, it's always a constant. In the starting of the lecture also, that means in the brief recap of the lectures, I already mentioned that the sum of radial and hoop stress is a constant. So it's a correct option. The radial and hoop stress does not vary individually. So it varies individually, but the summation is constant. That means suppose there is an increase of radial stress, that means there is a decrease of hoop stress, so that the sum is always a constant value. So this is incorrect option, because individually it can vary, but their summation is always a constant. The next option is sum of radial and hoop stress is not a constant. So this is also incorrect. Radial and hoop stress vary individually. So yes, it's the correct option, because radial and hoop stress can vary individually, but their summation is always. That means if radial stress increases somewhere, at that point hoop stress decreases, but their summation is always a constant. So this is the question number 7. Now move on to the next question, that is problem number 8. In case of warping of cross section, in case of warping of cross section, the first option is uz must be independent of r. uz must be independent of r, that means radial coordinate. Option B is ur must be independent of z. ur must be independent of z. The third option is ur u theta must be independent of theta. ur u theta must be independent of theta. The fourth option is none of these. So in this question, in case of warping of cross section, whenever we say warping, that means the planarity of the cross section will not remain. That means the cross section will become non-planar. Warping means non-planarity of cross section. So in case of warping of cross section, uz must be independent of r. So yes, it's a correct option, because in the case of warping, uz must be independent of r. That means uz should not be dependent on the radial coordinate, because suppose if uz depends on radial coordinate, so at every radius, at fixed radius, at particular cross section, and if we vary the radius, uz also changes. That means there is a different displacement happen at the same cross section. So suppose this is a cross section, and if we move along the radius, so at every radius there is a different z. There is a different z displacement. That means there is a out of plane deformation happen. The deformation is not remain planar, it will generally out of plane. So it must be followed that uz must be independent of r for the warping of cross section. The second option is ur must be independent of z. So this is not a correct option. The third option is ur theta must be independent of theta. It's also not correct. None of the above. Next, move on to the next problem, that is problem number 9. For the case of isotropic tube, for the case of isotropic tubes, u theta generated due to, the first option is extension, the second option is torsion, the third option is inflation, and the fourth option is none of these, all of these, all of these. So this question says, for the case of isotropic tube, U theta is generated due to, basically the displacement along theta direction is generated due to extension. No, due to extension there is no theta displacement occurs. So this is incorrect option. Torsion, yes, due to torsion U theta generated because there is a change of angle of the cross section. At every cross section there is a change of angle, so due to that the theta displacement also changes. So this is the correct option. Inflation, no, due to inflation there is no change in the U theta, there is a radial displacement happen in the case of inflation. So it's also an incorrect option. All of these is not the correct option because only one option is correct here. So it's also incorrect. Now the next question is problem number 10. So this is the last question which I will discuss now. Shear strain in case of extension, torsion, inflation of hollow cylinder in theta z plane is given by, the first option is 0, the second option is omega r upon L, third option is omega r upon 2L, and the fourth option is ur upon r. So the question is, shear strain in case of extension, I am repeating the question. Shear strain in case of extension, torsion, inflation of hollow cylinder in theta z plane. So in theta z plane, shear strain is given by in theta z plane, shear strain in theta z plane shear strain is given by gamma theta z is given by del u theta upon del z plus 1 by r del u z upon del theta. Okay, so del u theta upon del z, and what is u theta here? So u theta is given by omega by L omega by L into z. Okay, and use it for the case of, if we assume that there is no warping of the cross section, so uz is independent of u theta, uz is independent of theta, so this term will cancel out, that term only will remain. So half of what is del u theta upon del z is given by omega r upon L. So gamma theta z is given by half of omega r upon L. So the correct option is option number C. So this is question number 10, which is based on shear restraint along theta z plane. So this is all about today's session. So I will first I have first give the overview of the lecture based on the extension torsion inflation of hollow cylinder. After that I will solve the problem based on the torsion, extension, torsion, inflation. So I have solved two major problems. Problem 1 and 2 are very good questions based on this concept. Then problem 3 and 4 based on the numerical approach of torsion of shaft. And then problem 5 to 10 are the multiple choice question through which you can better understand the basic concepts. So problem 5 to 6 based on the basic concepts of these lectures. So yes, all of the problems, that is problem 1 to 10, are good questions. I hope you understand these questions, and if you have any doubt, please feel to write in the chat box in the YouTube channel, or you can also ask me in the next meeting, which will be conducted in the coming Friday. So this is all about week 8 live session. So thank you for joining today. You can leave the meeting now. Thank you.